Now we're going to take a look at the gyro sensor. And the gyro sensor basically measures degrees of rotation. And if you look at the top of the gyro sensor, it has a little Z on it, and it shows a circular symbol, which should be the top of the gyro sensor if you want to be measuring your robot turning this way. So make sure it's mounted that way. Now the gyro gives us a few advantages over using the drivetrain turn 90 degrees function. With the drivetrain function, as I've mentioned before, it's a mathematically calculated function that just that calculates based on your wheelbase, size of the wheels and other factors, how many rotations of the right-hand wheels forwards and the left-hand wheels backwards the robot needs to do in order to turn 90 degrees, which is fine, and it will be reasonably accurate. You will be able to use that function. However, if you're using a lot of them in an autonomous routine, you get what's called accumulation of errors. So let's use this robot to show an example. So I drive forwards, that's my first command. My second command is turn left 90 degrees. And so the robot turns 90 degrees. And maybe we got a little bit of slippage on the wheels. The wheels didn't grip completely. So the motors have turned through what it thought was 90 degrees, but the robot doesn't make a full 90 degree turn. Now there's no feedback to the robot from a sensor to let it know that. So it continues on, and the next move might be to go forwards to here, and then the next one is right 90 degrees, and from this point right 90 degrees will send us to here, and that might send us right to the right hand side of where we want to collect the balls. We'll miss the balls and not be able to collect them, and over a long autonomous period those errors can accumulate and get worse and worse. So with a gyro you can minimize the accumulation of those errors. And that's what we're going to show here. So the gyro sensor has some calibration and setup processes that need to be run before it can be accurately used, which means that the coding becomes a lot more complex than just using the turn left and turn right commands. However, for advanced programmers that will be useful because, like I say, you can reduce your accumulation of errors. So I've added a touch LED to my robot. You'll see why that becomes useful in a second. The touch LED has a rim here which we can illuminate a number of different colours, and on the top it has a touch sensor that will detect when I touch it. So I've mounted one up here on the top of my robot, and I'm going to use this to start my program. The reason for that is the calibration process of the gyro takes 3 or 4 seconds, and if you need to calibrate the gyro once your robot is on the field in the correct position. And at a competition, if you include that calibration in your main program, the match will start, the robot will sit still and calibrate for 3 or 4 seconds, and you've wasted that time before you can start moving. So the idea is you put your robot in position on the field and start the program running, and the gyro can be calibrated and ready. And then when you're ready to go, you let the referee know, and then you actually use your touch LED to start the autonomous routine, start the robot actually moving. I'm going to show you how to do that. So let's go into the blocks and look at the gyro. And in the setup section for the gyro, we've got these 2 blocks, calibrate and then reset angle and rotation. You can click on the little help files next to any box just to read a bit about it. And it says here, causes the gyro to perform a 3-second calibration. This calibration minimises errors in angle and rotation. Do not move the gyro during this command, and that is really important. So here's a little program to help you sort of set the gyro up. When the program starts running, we're going to calibrate. And at the same time, we're going to switch our touch LED on. So when the program starts, we're going to switch our touch LED on, and we're going to make it red as a warning symbol. So set that to red and switch it on. Back to the gyro. as we said, it takes 3 seconds or so to calibrate, so we don't want anything to happen. Well, I'm actually going to give it a bit longer than 3 seconds just to make sure. I'm going to give it 5 seconds, and what I'm going to do is put in a wait command. 5 seconds. And once that 5 seconds is complete, we're then going to reset the angle and rotation. What that means is that straight ahead on my robot becomes 0, 90 degrees to the left, 180 degrees to the back, 270 towards the ramp, and so on. And then I'm going to broadcast a command now. So create a new command here, new, and I'm going to say gyro ready. So the calibration is complete and the gyro is ready. When the gyro is ready, the touch LED can go green. So when gyro ready, set the colour. Then I want to use this button to start the match. So all of that part has happened. We've come to the field, put our robot down, started the program running, and it's gone through the calibration routine. And we then say to the ref, right, we're ready to start. And when the match starts, press this button, and that's when your robot starts moving. So to do that, we're going to put in a forever loop, an if statement. We want to say if we're pressing the touch LED, or if we're touching the touch LED. If you look under sensing on touch LED, you've got this box, touching. So if we're touching it, then we're going to break from the loop. If you remember that break command from earlier, so that will exit this forever loop. And then we're going to broadcast a command that says, create a new command, start moving. That's when the robot actually starts the autonomous routine. Now under the drivetrain block, we say when start moving, we want to drive forwards, and as per the previous program it was 400 millimeters to get us into the center of this square roughly. Now we need to make a turn, and we're going to use the gyro to do that. So rather than just saying turn left 90 degrees using this block, what we're going to do is use a while loop. And what we want to do is say while the gyro is less than 90 degrees, keep turning. So find our less than box. And under sensing and gyro, we've got angle in degrees and rotation in degrees. So angle in degrees is an absolute. So if you imagine if you put a 360 degree protractor in front of your robot, straight ahead would be 0, 90, 180, 270, 359, 0 again. That is useful in certain circumstances, but for what we're going to do here, when we say, we're going to say while the gyro is less than 90, then we want to turn left. Well, if we veer ever so slightly to the right as we're driving forwards, that value becomes 360. Or 359, and then that while loop will just exit and we'll never start turning left. So we're going to use the gyro rotation in degrees, which is very similar, apart from it gives you positive values counterclockwise and negative values clockwise, or start subtracting values clockwise. And that's useful because if the robot starts veering to the right when it starts, it will be -1 degree. And that's not going to cause us any problems because we still say, well, while it's less than 90, turn left, -1 is less than 90, that's absolutely fine. We'll start turning left. So get gyro rotation in degrees is less than 90. What do we want to do? We want to turn left, but not using a certain number of degrees. We just want to turn left until the gyro reaches 90 degrees and then stop. Okay, we'll download the program. And when I play, the touch LED goes red, and at this point if I touch it nothing happens because the gyro is busy calibrating. When it goes green, I can now touch this to start the program. Okay, so for something that's supposed to be really accurate, that's actually overshot our 90 degrees. Why is that? Well, it's the inertia. The robot's spinning, the robot starts spinning, and as it gets to 90 degrees, when it gets to that perfect 90 degree turn, it then switches the motor off. But there's still the inertia in the weight of the robot which carries it just past the 90 degrees. There's a few ways you can deal with that. You could set this value lower so that it was 88 degrees or something like that, but it doesn't really solve your problem because there are certain circumstances where you won't have that inertia. You really do want to actually turn 90 degrees. So what we want to do is turn slower. Now if we turn the whole 90 degrees slowly, it will take forever and we're not really gaining anything because we're just wasting time turning. So what we're going to do is actually have two loops. Break this one off. Make another while loop. It's very similar. So while gyro rotations is less than something, we'll work that out in a minute, we want to be turning left. Now what I'm going to do is I'm going to turn the first 60 degrees of my 90 at full speed. Well, actually it's not full speed. If you go to setup here, the default is 60, so we can turn 60% speed, turn speed. So, and that's what your default is set to. You can change this value so you can turn faster or slower. So the first 60 degrees we're going to turn at 60%. And then the last 30 degrees we're going to turn really slowly, just 5% turn speed. Okay, so when we start moving, we move forward 40%. Move forward 400 millimeters, set our turn speed to 60% and start the turn. When we get to 60 degrees, we exit this loop, set the turn speed to 5, and then the next 30 degrees, the difference between the 90 and the 60, we turn at just 5%, and then we stop. So let's give that a go. Download that whilst I'm repositioning the robot. But I don't want to run it until my robot is in position and square with the back of the field, because as soon as I start running it, my gyro is going to reset. So gyro calibrating, execute the program, start the turn at 60%, and then finish it at 5%, and then we get our perfect 90 degree turn.